Hello, welcome to this video about reaction rates and equilibrium. In this video, we're going to look at factors affecting the rates of reaction. We're going to look at something called chemical equilibrium and reversible reactions. We're going to also look at Le Chatelier's principle. And to give you a little preview, here is an example of a reversible reaction. It's so cool. We have a cobalt compound that's pink and then a cobalt compound that's blue. And these are reversible. We can take this and by adding certain things, we can cause it to turn blue, and adding different things, we can cause this to turn right back into that pink cobalt compound. As you may have guessed, a reaction rate is simply the rate at which reactants change into products. How fast does this reaction proceed? How fast does it go? Well, what factors might affect the rate of reaction? I'm sure you've got some really good ideas, and before we talk about them, let's look at what we call the collision model of a reaction in chemistry. The collision model of a reaction states that atoms, ions, or molecules must collide in order to react. We actually have to have a collision or there will not be a reaction. In other words, this nitrogen monoxide must actually collide with this ozone molecule in a collision in order for the reaction to occur. That energy in the collision itself is what breaks the oxygen-oxygen bonds in the ozone, and it allows an oxygen-nitrogen bond to form, a new oxygen-nitrogen to form, to make this nitrogen dioxide, and diatomic oxygen is left over. So since we can think about reactions as occurring because of that collision model, because they're actually bumping into each other, the molecules or the atoms, we can now talk about what is affecting reaction rates. Let's look at a lot of different factors. One is temperature, and you probably know that because you can speed up a reaction by heating it up. You can see on this graph that this is the case for this particular reaction. As it proceeds, we have this higher temperature and this lower temperature, and the higher temperature is producing product at a faster rate than this lower temperature. Why does temperature increase the reaction rate? Well, remember what temperature is. It's a measure of the average kinetic energy of all the particles. So if we raise the temperature, we have particles moving faster. It means they're colliding more frequently, and they are also colliding with greater energy. As a result, we have more collisions resulting between colliding particles and collisions that are happening with greater amounts of energy in any given amount of time. So it increases our reaction rate. The concentration of a substance also affects the reaction rate. Concentration simply describes the number of particles of a substance per unit volume. So here we have low concentration, we have fewer particles for this particular amount of volume. Here we have a higher concentration, more particles per volume, that amount of volume. In the lower concentration, we're going to have fewer collisions. Higher concentration means more collisions. For chemical reactions that involve gases, volume and pressure are important considerations, and they certainly affect the reaction rate. If we look at this gas here and we decrease the volume, you can see that decreasing the volume is going to increase the concentration of the gas, and that will increase the reaction rate. Also, as we decrease the volume, we are increasing the pressure. So an increase in pressure will also increase the reaction rate. The converse of that is true. If we increase the volume, we are going to lower the reaction rate. Or if we decrease the pressure, we will also lower the reaction rate for these gases. Surface area also affects reaction rates. You know that because when you try to dissolve sugar cubes in water versus granulated sugar, it will take a lot longer for that sugar cube to dissolve. And even though that isn't a chemical reaction, that is simply dissolving, we can think of a similar thing when we talk about a reaction. You know that if you have a lump of something here, particles that are trying to react with this substance, they're going to be able to react with these atoms on the outside, but they won't be able to react with the molecules in the center of this lump. So if we have greater surface area like this, and if these were spread out and we had a lot more surface area, then the reaction rate would go up. In this case, the reaction rate will go down because we only have the surface area on the very outside that can react with these particular species on the outside. A couple of other things to consider. Catalysts also will affect a reaction rate. A catalyst is a substance that can be added to a chemical reaction that will speed it up, but it isn't being used up in the process. It itself isn't being permanently changed. An example of that, enzymes in biological systems are critical for all sorts of chemical reactions that occur in organisms. An inhibitor is also something that can be added to a chemical reaction, and it will slow a chemical reaction, sometimes prevent it entirely. An inhibitor example would be food preservatives. They are added in order to slow the process of the chemical reaction of food spoilage. Now let's take a little look at reversibility. Can a chemical reaction be reversible? We've talked about this a little bit before, but yes, indeed, they can. We can actually have chemical reactions that move in only one direction. An example for that would be, obviously, this combustion reaction is not reversible, is it? Kind of like traffic, and only going in one direction. It will not go back into those nice little logs that you started out with. Or we can have a chemical reaction that can move in both directions, like this traffic. We call that, if it can move in both directions, a reversible reaction. Here's an example of a reversible reaction. It can proceed this direction, or it can proceed in the reverse direction. A reversible reaction is designated by the arrows going both this way and in the other direction. Now, since you know about reaction rates and you know that there are reversible reactions, we can now talk about something called chemical equilibrium. Chemical equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction for a reversible reaction. Now let's take a look at this example to help make this clearer. Let's say we have some water and it is undergoing vaporization. We have it changing from its liquid state into its gas state. Now that's not the only thing going on, because we also will have, after we have these molecules in the gas state, some of them are going to change back into the liquid state via condensation. So we have molecules going from liquid to gas, but we also have some molecules going from gas back into liquid. And at a certain point here, a little while later, we're still having the vaporization rate here is still greater. See, more of them are going this direction than the condensation rate. It's just only a few going that direction, the reverse reaction. But after a certain period of time, we are going to get the rate of molecules vaporizing being equal to the rate of molecules condensing. It does not mean that the volume or amount of liquid is equal to the volume or amount of gas. It means the rate that the molecules are going in this direction is equal to the rate that they are being converted back in this direction. That is really the important key behind chemical equilibrium. The rate of the forward reaction is equal to the rate of the reverse reaction, not the amount of products or reactants or anything. It's simply that the rates are equal. It's a dynamic state where all of the concentrations of reactants and products will now remain constant. Since these rates are equal, the concentrations of the products and reactants will at that point remain in a constant state. Now let's take a look at what happens when a change is imposed on a system at equilibrium. What if we change the concentration? Or if there is a change in the pressure or volume? or we're carrying on a chemical reaction and we change the temperature. For reactions that are in a state of equilibrium, where we have the rate of the forward reaction being equal to the rate of the reverse reaction, and we change something about it, we make a change to the system, we have Le Chatelier's principle to help guide us. Basically, what happens in a reaction when we make a change to it while it's happening? The position of the equilibrium will shift in a direction that reduces the effect of that change. So let's say we have our equilibrium. We have our reactants and our products, and they're in equilibrium. The forward rate is equal to the reverse rate. But we dump a bunch of reactants onto our system. We add more reactants. And look, we're tipping the scale. We have a lot of reactants here. You know what happens? This reaction will shift to the right and produce more products so that it is balanced again. It reduces the effect of that change. Here is an example. We have nitrogen and hydrogen reacting to produce ammonia. And in this reaction, let's say we're carrying this out, these are all gases, and we add a whole bunch more hydrogen, put a bunch of hydrogen into our system. You know what happens? The reaction shifts to the right to compensate for that, and more product is produced. What if we change the temperature? Again, the same thing happens. The equilibrium is going to shift in a way that reduces the effect of the change. If we think about temperature as energy, this is the reaction. It is producing energy. So energy is thought of as a product. It is an exergonic reaction. Energy is being given off. What if we take energy out of the system in this example? That would be like removing some of the product. If we say minus product, well, that's going to make the reaction shift to the right because we are removing products, and so the reaction will shift to the right to compensate for that. So if we remove some energy, we're going to produce more product. What if we change the pressure or volume? And this would be for a reaction that involves gases, like our example here. Again, the position of the equilibrium is going to shift in a direction that tends to reduce the effect of that change. So remember, for gases, if we decrease the volume, like this, we're going to increase the pressure. And our reaction, if we decrease the volume and or increase the pressure, a reaction is going to respond to reduce that pressure. It doesn't like the pressure. So for reactions involving gases, decreasing the volume or increasing the pressure is going to shift the reaction to the side with the least number of gas molecules. That will help reduce the pressure. So let's look at this example. What if we decrease the size of the container, decrease the volume, and thereby increase the pressure of this whole reaction? This reaction wants to reduce the amount of pressure, and it's going to shift to the side with the least number of molecules. You can see that this side of the reaction has one gas molecule right here. There's one N2 molecule, but there are 3 diatomic hydrogen molecules. That means there are 4 gas molecules on this side. There are only 2 gas molecules on this side, 2 ammonia molecules. So this reaction is going to shift to this side because it wants to reduce that pressure. So it will shift to the right and produce more product if we reduce the volume or increase the pressure. If we do the reverse of that is true. The reaction will then shift to the side with the most number of gas molecules. Advanced ideas. Try some of these more interesting problems here. See how the reactions shift in those problems, or look up who Le Chatelier was. Who was this guy? What were his most famous accomplishments or other accomplishments in life? Any other interesting facts about his life? Look forward to seeing what you come up with, and we'll see you in class.